Good evening, everyone, and welcome to Astronomy at the Beach 2020. I know this year is virtual, which is a bit weird for all of us. No going out to the field at the park and looking through telescopes, but we're going to do what we can to do events virtually here for you. So our first event for this evening is from the Ford Club is Mike Bruno, and Mike Bruno is going to talk about the size and the scale of the solar system. So without any further ado, I hand it over to Mike. Mike, it's all yours.
All right. Hi, everybody. So if you've been to Astronomy at the Beach before, you might have seen me out there with a big, gigantic yellow beach ball. And so, like Liam mentioned, we're broadcasting from our local locations. I'm in my garage in Dearborn. So right here in front of me, I have my scale model. So I was always interested in the size and distances of like the planets I was observing through either binoculars or telescopes since I was a kid. And I decided to do some math and look up some calculations to see how far away things were, how big they were, and what size the Earth is compared to all the objects in the sky. And so I found myself a blue marble. So of course you can't see it right now, but this little tiny blue marble is the size of the Earth. It's a 1/2 inch in diameter. And we have the sun here. It's a 1/2 mile. It's 5 feet in diameter. So this is an actual true scale. I actually got out my calipers and I measured everything and tried to get this thing as close as possible. Right now I have some of the planets in front of me, and I went and just found different common objects that everybody's familiar with to build this scale model. I can't even remember when I designed this now. It's been some years. Pluto was actually still a planet. It's still on my scale, and I'm keeping it there. But because I like to interact with people when they came to see me, and we would just talk about general facts, and some people would spend a couple minutes, some people would spend longer with me, and we talk about different things. I have a little presentation I'm gonna talk about right now. I'm going to share my a PowerPoint presentation I have just to kind of go over some interesting facts and like numbers, I guess you could say, to try to make you understand like really like the little tiny Earth we live on is really something special compared to how big our solar system really is and how far away things are. So give me a second here. I'm going to go ahead and share my screen.
So while Mike is doing that, I just want to remind everyone, please, there's a little like button below the YouTube view. So click on the thumbs up and subscribe. It's a good idea. And I would also recommend, please feel free to ask questions in the live chat. We will answer questions as the presentation goes on.
Where the heck's play on this thing?
On your slideshow, Mike.
Is that down here at the bottom? Yeah.
The next one. Yep. There.
Okay. All right. So I've done various presentations in the past with the scale model for scout groups and for our local astronomy club. Oh, that's another thing, Liam. Maybe mention or put in the comments on the YouTube. We're all members here of the Ford Amateur Astronomy Club. I'm the current president, so maybe put our website link out there every once in a while. People, if they're interested, can look us up. We're in Dearborn is where we meet when we get together. Okay, so back to it. So what if the Earth was a blue marble, right? So I don't know if you heard that term before, but I found that this little blue marble one day, and it got me thinking. And so I started building the solar systems model across that. So here's a neat picture I found online. So I have some various sources, because Google's wonderful, to kind of take a look at how big the sun is compared to where our little tiny Earth is, if you can see it pointed out there, compared to the other planets. Little background. So astronomy, it's the study of matter in outer space, such as the planets, stars, galaxies. And so because the solar system is, near and dear to us, it's not too far away, relatively speaking. I'm going to talk about the solar system. It's divided into two groups. We got the four inner planets, Mercury, Venus, Earth, and Mars. And when I made this again, Pluto, five outer planets. Okay, so we got Jupiter, Saturn, Uranus, and Neptune. And the outer planets, really the four now, are gas giants. And you'll realize like the really giant is Jupiter. So we'll talk about that in a minute. And the other parts of our solar system are things you hear about in the news lately. We had Comet Neowise come by. So comets, they come around all the time. Some are small and you don't really see them, and they don't really put on a big show like we had recently, which we were lucky to have. The asteroids, you probably hear about that a little bit. Some close flybys of asteroids coming by the Earth. I think there was one that's coming or just came the size of a bus. It was like it went within 13,000 miles, which is inside the orbit of the Earth and the moon. So that's a pretty close flyby. But actually also asteroid that size kind of hits our atmosphere every other year. So that's kind of interesting. And there's things that, we got the moons and the far out objects too. There's different parts of the solar system I'll talk about. So I really like this picture. It's images, probably space telescope images of the outer planets and Earth, and of course the other inner planets. And this is kind of relative to scale. So
Mike, a question for you.
Oh, sure.
We all see images like this all over textbooks and on the internet and so on.
Mhm.
Like, let's tell everybody how it really is laid out.
With what?
How, like, we all see them really close together in the book
Distance.
and so on, in distance wise.
Oh,
Yeah.
the distance. Yeah. So, yeah, like there's only certain things you can do with a scale. You can do size or distance. So this is size. So this is in order, but the distance is pretty extreme. So I'll talk about like the distances on my scale at least to try to get it relative. So I'll give you like some big numbers, and that's the thing that's confused me also over time is you're talking about millions, like oh, you heard a million, whatever, but you don't realize like how long it would take you literally to count to a million. And then we're talking billions and with some of the other distances with like, for instance, Pluto, it's, almost 4 billion miles away. So it's hard to wrap your head around that. So on my scale, though, I shrink it all down and I'll give you some representations of like, oh, we got this 1/2 inch Earth. So how far away is it from the sun? So it's about, we'll get to it, but I'll let you know a little insider info now. It's about 2 football fields away.
I was just going to say that if all of these planets were lined up on your computer monitor, spaced out accurately, but then set to their appropriate size, only the sun would be visible. No other planet would even be a single pixel.
Right. Yeah.
Not even Jupiter. Yeah.
I think the sun maybe would be a pixel. I think I've seen something like that.
Yeah.
And so that is kind of interesting too. And then it's almost too small to comprehend. So, it's kind of interesting to think about that. Like when you're just standing on your big Earth, like, oh, I'm on this gigantic planet, but then it's like, well, it's all relative. So, but so moving on. We got, of course, the sun, which we all know and love because it keeps us alive. And it is truly massive. The sun is actually colorless. Now, you saw my scale, my little model here at the beginning. It's yellow because everybody thinks it's yellow. But it's a combination of all the colors in the spectrum that we can see. So that creates white. So technically, the sun is white. It's also 99.86% of the mass of the solar system. So when you think about that, whatever you want to do, if you want to think about building a model like that, take yourself a pound of something or 30 pounds or whatever, like 99.86% is everything. We're the leftovers. So I like telling people that, like, even Jupiter, as big as it is, Jupiter Let's see, the mass of Jupiter. I had it in front of me. I don't know what I did with it. So anyway, the mass. Oh yeah, Jupiter is like 70% of the remaining mass of that 99.86. We're really just the leftovers of the sun of the solar system. It's really crazy to think about.
Which is really something, because if you add all the other planets together, even though visually it doesn't look like it, but if you add all the other planets and all the asteroids and all the Kuiper Belt objects and all the little dust specks that you could find and add them all up in one clump on one side of the scale, Jupiter tips the other side of the scale easily, right? It's more mass than everything else added together, excluding the sun, of course.
Excluding the sun, yes. All the objects in the entire solar system would fit inside Jupiter. That's how massive it is. It's really, really big, and it's really it's a sentinel out there too for us. Where its location is, it's protected Earth over the years in general. Maybe the one got by that wiped out the dinosaurs, but it's kind of like a vacuum cleaner out there too, and especially the life where we are at in our solar system right now. Jupiter's done a wonderful job in protecting the Earth and the other planets. So let's see. So the sun's gigantic. This is just a little quick frame. I don't want to get into too much, but the surface temperature of the sun is around, I think it's about 10,000 degrees or something like that. But the core, it's as you can see there, that's in Kelvin, but it might as well be, doesn't matter. It's 15 million degrees. It's really, really hot down there in the core. You can do some, like if you didn't get it today, tomorrow, maybe starting at 3 o'clock, we have white light and H alpha viewing of the sun. I think I heard there was a sunspot out there right now. So the sunspots, that's a H alpha view of the sun here. You can see that like cooler regions on the sun. They're also gigantic because, the Earth is, you could take 109 Earths and go across the diameter of the sun. And the sunspots, they can be 5-10 size the diameter of the Earth. They're gigantic because, you're dealing with a gigantic object.
So Mike, you quickly uttered the phrase H alpha. So what's H alpha?
Yeah, it's a special wavelength for viewing the sun. I'm not very technical in it, but the H alpha wavelength is where you can see this picture here, the solar flares. So solar flares are visible through that hydrogen alpha wavelength, and you need a special telescope. And I guess I should mention, like we always try to, is you only use special equipment to look at the sun. Do not use a regular telescope. They have special filters. So a special telescope called hydrogen alpha, you're able to see the surface of the sun. So you can see the solar flares and prominences. So the flare here, it just kind of shoots up and they last just minutes sometimes. A prominence is much larger. They kind of are, it's a cooled arching of gas ejecting from the sun. So it will create an arch or a loop. And some of those can be 100, the typical is about 100,000 kilometers. So that's 10 times the size of the Earth just there. And so, some gigantic ones can be 500,000 kilometers. So it's very, again, the scale, it's huge compared to the little Earth. And if you can see the little Earth in the top right, that's just kind of a scale. Actually, I don't even know, that might be a little wrong. I think it's trying to measure really the flares, though. That's what that's for, is kind of how big a flare can be.
Yeah, I sometimes talk to the students and I say, imagine if you had a flamethrower and while standing in Michigan, your flamethrower was so powerful that you could hit a spot in the middle of Australia. That would be a pretty powerful flamethrower. Now, multiply that by 5 or 10 or 20. And now you're starting to get to size some of these loops that are just absolutely massively bigger than our entire planet.
Yeah, it's amazing. And like here you have something called the coronal mass ejection. They don't happen all the time. When they do, you kind of want the sun to be pointing on the, away from the Earth instead of the Earth. But it really can cause for some technical difficulties if it's very gigantic, but it also can cause some great aurora. We can talk about that in a brief second. But it's kind of like a hiccup, really. That's how I want to call it for the lack of a better technical description. But that ejects the mass from the sun, and sometimes the Earth is in the path of that. And as you can see how gigantic that is on this image here, I couldn't imagine how many Earths it would take to span that distance there. And then here's some beautiful aurora pictures. It's the solar wind interacting with the Earth's magnetic sphere. And the further north you are, the better odds are you have to see it. And our sun also has a certain cycle where it's more active than other times of the year. It's 11 years. They call it the 11-year solar cycle, from minimum activity to more massive activity. So it rises, peaks, and starts over every 11 years.
Yeah, it's actually coming out of its dormant phase right now and starting up the new solar cycle. So activity is starting to increase.
Excellent. Yeah. Yep. So some interesting scale facts here compared to the Earth. The sun is 865,000 miles in diameter. The Earth's just under 8,000. Like I said, 109 Earths to span the sun's diameter. Another crazy fact, I like having people guess, but I'm going to give you the answer now. You can take 1.3 million Earths to fit in the sun. So like, oh, wow, that's a big number. But then when you're standing at my table and we're talking about it and I'm holding this 1/2-inch blue marble, telling you like, yeah, 1.3 million of these things. Literally, if I had 1.3 million marbles, it would fill up that, I guess, lack of a better word, a beach ball, which is now the sun.
And you'd still have room to swish them around.
You would have some room to switch them around. And that's just to fill the mass. I think the weight, it's even there. It'd take even more.
Yeah.
So, let's see. So you hear sometimes in astronomy the term astronomical unit. So talking in miles, it's about 93 million miles. That's the average distance between the sun and the Earth. The Earth orbits on an elliptical, kind of like, you want to say it's like a ellipse is like an egg shape, right? But when you think of an egg, that's like a big ellipse. The ellipse of our orbits, even though they have like a farther point and a closer point to the sun, and it's measurable, it's still, if you looked at it on any type of drawing, it would look like a perfect circle, really. And then a couple other fun facts I like to bring up and talk to the kids. Say, so if you hopped in your car and you took that one-way trip to the sun and you were doing 70, it'd take over 150 years to drive to the sun on that one-way trip.
So you should definitely use the bathroom now.
Yeah, use the bathroom, stock up on snacks, hopefully you have a Tesla or something, so you can maybe get some good, maybe renewable panels or something to keep your power going. But yeah, it's 151 years. The light from the sun, even though it's like, oh, the sun, you see it all the time, that's still 8 minutes old, the speed of light. But it's when you kind of bring it down to like, your Earth everyday life of 70 miles an hour, it's like, that's a crazy distance to think about.
I like to use airplanes. So a 747 on a one-way trip to the sun, if you could do it, it would take it 20 years to go one way.
Yeah.
And the Blackbird, which is the fastest plane that we got,
yep.
The Blackbird can make it there in 16 years. And that's a one-way trip.
Yeah, yep. It's one way that the sun will suck you in too. When you get there, it's so massive. So the marble again, so now to bring it down again, we've talked some big numbers, but it is, I said earlier, it's about 2 football fields away, 550 feet. So at least on this scale, you can say, oh, okay, I see this 5-foot beach ball. and your half-inch marble. But, you know, run out 2 football fields and that's where this marble is. So it's, you know, there's a lot of emptiness in between just this marble and this massive sun. And it's so massive, we're in orbit around it. So this tiny little marble is affected by that gravity of that 5-foot beach ball. It's crazy, crazy to think about. So, but moving on, let's talk about some of the planets in general. There's a great picture of the Earth. I wanted to just kind of, before I moved on, I found this picture, and this is kind of a scale also, and it's all the water on the Earth. And so when you think about all the oceans, how deep they are and everything, and all the water, and then you look at this, you're like, wait a second, that's kind of not that much water. So it's really like we're like an onion. The water is like an onion layer on the top of the Earth's surface. And that first big bubble is all the water. The next big bubble is all the fresh water. And there's a really tiny one just above Florida. And I'm sorry, all the water which is in the glaciers is in the first one. Then all the second one would include the oceans. And the third one is all the fresh water. So that's a tiny dot, you can, if you can see it, is it's like 2.5% of all the water on the Earth is just the fresh water. And you know, there's also water underground that's included in that. So, and the Great Lakes, I don't think I wrote down that fact, but they account for a lot of the fresh water that's available. It's crazy, and we're just surrounded by them.
You're on mute, Tim, if you're trying to speak.
So I was just going to say, Neil deGrasse Tyson did a really cool analogy on that. If you can go back to that dry Earth, you see these classroom globes, and they have the bumpy textures, you know, to show where the mountains are. And he says, and they're really misleading because you got to think of the fact that with a planet that has a diameter of almost 8,000 miles, so about a 4,000 mile radius, right? The tallest mountain, 5 miles, right, up, and the deepest trenches in the ocean, 3 miles deep, I think, is nothing, you know, not even a percent of 4,000 mile radius. And he says it's so little that if you took a classroom globe and took just your finger, and you've got, look at the little ridges on your fingerprint, because if you were to press your finger onto the classroom globe, but it was actually a real Earth that small, he says you know, the ridges on your finger would be touching the bottom of the ocean, and the little grooves, the top of the grooves wouldn't even be wet yet. He says that's how thin the water is.
Yeah.
We think of the ocean as deep, but he says it's really not that much.
Yeah, it is crazy, but we're tiny on the scale, right? So it's all, again, just like with the Earth compared to the sun, you know, us compared to the Earth, you know, we're like a microbe. So it's crazy. So moving on here with a little bit of facts on the planets. One thing when I was investigating, you know, the scale and finding the diameters and mass of everything I was looking at, I was like, I always knew Venus was around, you know, kind of like the size of the Earth. So Venus is 95% of the diameter. Mars is 53% and Mercury's 38%. And I was surprised how little Mars is on the scale. Because when you're looking at something 2D, you know, oh yeah, I get it. It's 50, you know, it takes 2 Mars to go across the Earth. But when you're looking at in the 3D that I have here with these little objects that you'll see shortly, you're like, wow, Mars is pretty tiny compared to the Earth. And I always thought that was kind of interesting thing to see when we talk about all these probes that flew the Mars and how far away it is to get these probes there to land on Mars and investigate Mars. Like the scientists, there's some smart people because it's amazing what they accomplish, even, you know, going to our own moon. So a couple of quick things is, you know, Mercury and Venus are inside the orbit of the Earth. So they rotate around inside. And Mercury is an odd planet. It takes 88 days, Earth days, to go around the sun. So that's pretty quick compared to our 365. But the go one revolution, so a 360-degree turn, it takes 59 days. So that's like, oh, wow, it's almost a year. But really, the Mercury day, so it's kind of hard to visualize. The day is really 176 Earth days. So that's going from the sunrise, the sunset to the sunrise in the same spot on Mercury is 176-day cycle. So it's kind of almost locked in orbit, kind of like how our moon is. You only see the one side of the moon. You know, Mercury's not quite there, but it pretty is. It's pretty close. Also, it's a very hot planet, but Venus is hotter. So you might have heard that. So Venus is around 895 degrees is the temperature. That's pretty hot. You don't want to be going there for vacation. And Mercury, though, it's 750 on a hot day, and then at night it's minus 320. So it doesn't look like a couple planets that you want to go visit. But because they're inside the orbit, there's a tilt on our orbit, on each planet's orbit a little bit, and Mercury can transit across the surface of the sun, or it passes between the Earth and the sun, and every once in a while it lines up perfectly where you can see Mercury cross. It looks like it's going across the sun. So Mercury does that about 13 or 14 times every 100 years. We just had a transit last year, and it's usually 6 or 7 years away, but every once in a while there's a 13-year gap, and we're into that 13-year gap. So if you didn't see it last year, the next one is November of 2032. And it is unique because it looks like a little sunspot going across the surface of the sun. And it's worth, if you ever get out to see that in 12 years from now, to try to do that. Unfortunately, Venus, it's a little bit different, and it has a weird cycle every 243 years or something, and it comes like 2 times within 7 years, and then it takes some time off. So that next time isn't until like 2117. So maybe some great grandkids of yours or something will see it. Also, another fact about Mercury is it is smaller than 2 of the moons in our solar system. Ganymede, the largest moon in the solar system, is around Jupiter, is bigger, and Titan, the moon around Saturn, is also bigger. And Mercury's almost the same size as Jupiter's second biggest moon, Callisto. So even though this is a planet that orbits the sun, there's some moons that orbit other planets that are bigger than Mercury. As well, you know about Pluto being a little bit tiny. So,
Mike, we have about 2 minutes left. So,
oh, okay.
So if there's any final points you want to write up, or if anyone has any questions, please chime in now. We will be going to live views over Michigan next with Gordon Hansen in a few moments. So if you find it on that link on the GLAC website. So do you have any final points, Mike, that you want to cover?
Well, I just wanted to show the scale here. So this is my model. The one thing I like to point out too is a man has only traveled 17 inches on my scale. So I thought that was pretty interesting because the distance that they're looking to travel to Mars is 838 feet on my scale model. So let me just stop sharing at this point because I think this is a good cutoff point anyway. A lot of people know a lot about the gas giants. It's worth looking at them right now. This time of year is a great time. But right now, here's my model. As you can see, Jupiter's a Spalding basketball sponsored by the NBA. We got another one here, Saturn. I like to point out that the rings on Saturn, if this was to scale, would be thinner than a tissue paper because in reality, the rings are only 1 kilometer in diameter around the gigantic Saturn. So that's kind of weird how thin they are compared to everything else. And although we call these gas giants, Uranus and Neptune, these are little racquetballs. On the scale, they're a lot smaller compared to the other 2 big giants that we have here. So, and one last thing is we talked about distance a little bit. So Pluto, I like to point out, it's over almost 4 billion miles away. On my scale model, you can't really see little Pluto here. It's kind of it's a little pebble. I'm not sure if we can get that or not. There's a little pebble here. That's 4 miles away on my scale. So quickly, this is a half mile away. This is a mile, 2 miles, 3 miles for Neptune, and 4 miles for Pluto. So this sun we have over here, this 5-foot diameter beach ball, basically, can keep something in orbit, and that's just Pluto. There's stuff that goes out a light year, and a light year on my scale goes out to about 28,000 miles, and then we start getting into big numbers again. But I appreciate everybody that came out tonight to watch this presentation. I hope you go take a look at Gordon. He's a wonderful astrophotographer. And I'll be back tomorrow also to talk about the scale. Maybe I'll have some other interesting facts to talk about that I didn't tonight. So thanks for coming out, everybody. And clear skies to everybody, and have a good night.
Thank you, Mike. So we're going to switch. We're going to end the stream, switch over to Gordon Hansen. So please find the link for Gordon Hansen's event, and we'll see you over there in a moment. Thank you.
Liam, Gordon is 10 p.m. Eastern start time, about 1 hour from now.
Oh, it's about an hour. I thought it was starting at 9. Oh, my mistake. I'm sorry. So we have an hour of a gap. Forgive me. So I kind of rushed you, Mike, a little bit. So if you want to add more, you can, because we have a gap. I thought it was 9.
You know what? I think it was fine. I concluded in a good spot, I believe. And maybe I made people want some more, and they'll come back tomorrow. I believe I'm on at 6:30 tomorrow.
Okay.
So I'm happy to conclude tonight, and I appreciate all you guys' support and helping make this happen. Thank you.
All right, guys. Thank you all for joining us. And we'll see you later on at the live viewing of the night sky with Gordon Hansen. Thank you.